Recall that the sum of a series is equal to the limit of the sequence of partial sums. So when we define the Bessel function in example 3 as the sum of a series, we mean that for every real number x, j sub naught open x close equals the limit as n approaches infinity of s sub n open x close, where s sub n open x close equals the sum from I equals 0 to n of open -1 close to the power I times x to the power 2I over 2 to the power 2I open I in factorial close squared. The first few partial sums are s sub naught of x equals 1, s sub 1 of x equals 1 minus x squared over 4, s sub 2 of x equals 1 minus x squared over 4 plus x to the 4th power over 64, s sub 3 of x equals 1 minus x squared over 4 plus x to the 4th power over 64 minus x to the power 6 over 2304. S sub 4 of x equals 1 minus x squared over 4 plus x to the 4th power over 64 minus x to the 6th power over 2304 plus x to the 8th power over 147,456. See the figure in the sidebar. Figure 1, partial sums of the Bessel function big J sub naught. You have curve S1, S sub 1, S sub 2, S sub 3, S sub 4, and J sub naught, big J sub naught, and line S sub naught. Anyway, back to the text. Figure 1 shows the graphs of these partial sums, which are polynomials. They are all approximations to the function big J sub naught, but notice that the approximations become better when more terms are included. Figure 2 shows a more complete graph of the Bessel function. For the power series that we have looked at so far, the set of values of x for which the series is convergent has always turned out to be an interval, open bracket, a finite interval for the geometric series, and the series in example 2, the infinite interval, open, -infinity to infinity, close. In example 3, and a collapse interval, open 0 and 0, close, equals the set of 0 in example 1, close bracket. The following theorem proved in appendix big F says that this is true in general. Sidebar, see figure 2, where y equals big J sub naught of x. Number 4, a theorem. For a given power series, the sum of n equals 0 to infinity of c sub n of open x minus a to the power n, there are only 3 possibilities. Number 1, the series converges only when x equals a. Number 2, the series converges for all x. Number 3, there is a positive number, big R, such that the series converges if the absolute value of x minus a is less than big R, and diverges if the absolute value of x minus a is greater than big R. The number big R in case 3 is called the radius of convergence of the power series. By convention, the radius of convergence is big R equals 0 in case 1 and big R equals infinity in case 2. The interval of convergence of a power series is the interval that consists of all values of x for which the series converges. In case 1, the interval consists of just a single point a. In case 2, the interval is open negative infinity to infinity. In case 3, note that the inequality of the absolute value of x minus a is less than big R can be written as a minus big R is less than x, and x is less than a plus big R. When x is an endpoint of the interval, that is, x equals a plus or minus big R, anything can happen. The series might converge at one or both endpoints, or it might diverge at both endpoints. Thus, in case 3, there are 4 possibilities for the interval of convergence. Open a minus big R and a plus big R, close. Open a minus big R and a plus big R, close bracket. Then open bracket, a minus big R and a plus big R, close. And we have open bracket, a minus big R and a plus big R, close bracket. The situation is illustrated in figure 3. Convergence for the absolute value of x minus a is less than big R. See figure 3, and divergence for the absolute value of x minus a is greater than big R. We have a line with an open interval at a minus r, a point a in the middle, and another open interval at a plus big R. We summarize here the radius and interval of convergence for each of the examples already considered in this section. The geometric series, we have columns, then there's the geometric series, example 1, example 2, example 3. We have the series column, a radius of convergence column, and an interval of convergence column. In the geometric series, where n equals the sum of n equals 0 to infinity of x to the power n, the radius of convergence equals 1, and the interval of convergence is open minus 1 and 1, close. And example 2, where the series is the sum from n equals 0 to infinity of n factorial to the power x, restarting again. Example 1, the series, the sum from n equals 0 to infinity of n factorial times x to the power n, the radius of convergence is 0, big R equals 0. And the interval of convergence is open curly bracket, 0, close curly bracket. In example 2, the series is the sum from n equals 1 to infinity of open x minus 3 closed to the power n over n, and the radius of convergence equals 1. The interval of convergence is open bracket 2 and 4 closed. In example 3, the series is the sum from n equals 0 to infinity of open negative 1 closed to the power n times x to the power 2n over 2 to the power 2n open n factorial closed to the power 2. The radius of convergence is big R equals infinity, and the interval of convergence is from negative infinity to infinity. In general, the ratio test, or sometimes the root test, should be used to determine the radius of convergence. The ratio and root test always fail when x is an endpoint of the interval of convergence, so the endpoints must be checked with some other test.